Okay, welcome to your second day on transformations. I want to go back and hit something on rotations that I told you your teachers may talk about, and I'm going to go ahead and put it just on this first page in the video so it's not a part of your notes. But if you remember, I talked about how to find it if you needed to just be able to rotate it, and I taught you that. The other method that there is to teach this, which is easier for some people, is to list your coordinates. The coordinates here are positive. Over here you have a negative followed by a positive. Down here all of these coordinates in the third quadrant are negative, and finally in the fourth quadrant they are positive. So you kind of use that, and then on this like 90 degrees and 270 you always have to flip the order of your letters. So we're going to see that our rules work doing it this other way. So if I want to go 90 degrees counterclockwise, I would take this and I'd rotate it. That puts me into that quadrant right there. So you can see that my signs have to be a negative followed by a positive value. And my original point was right here at 2, 3, 1 over 2 up 3. So when I rotate it 90 degrees counterclockwise, I'm going to get my value of -3, 2, because I flipped the order of my two signs, and then I change my coordinates are -3, 2. If I wanted to go, let's say 270 clockwise, then that would be 90, 180, 270. It's going to land me over here, so it's the same one I just did. It's going to land me at the same spot. My coordinates are still going to be negative, positive, and I still flip my original point of 2, 3. Now, if I'm going to go, I'm going to pause for 1 second and clear off that part of it. Okay, if I want to take this point and I want to rotate it 180 degrees, remember it doesn't matter which way I go. 90, 180 is going to land me in that quadrant, or if I start here, 90, 180 is going to land me in this quadrant. So I know that this one, both my answers have to be negative. I do not flip the numbers around, so they stay -2, 3. And then finally, if I were looking for a 270 flip, I'll pause, and a 270 would be taking it and going counterclockwise, 90, 80, 270. Notice my values are positive and negative, so I know my second value has to be negative, and I flip the order, so 3 comes first, 2 comes second. If you compare to last night's notes, you'll see that you end up with the same thing. Okay, we're going to move right along into symmetry. Symmetry just basically tells me I'm going to take a figure and kind of cut it right down the middle. The formal definition is a figure in a plane that has a line of symmetry if the figure can be mapped onto itself by a reflection line. So basically it's going to be the line that divides it into two. So I just have some pictures up here so we can see how many lines there are. So kind of pause for a minute and see if you can come up with it on your own. In this particular one, there's 1, 2, so there's 2 lines of symmetry. On this one, this is a hexagon. Notice all 3 of these are hexagons, but they don't have the same amount of lines of symmetry. So this one has 1 going this way, 1 going this way, 1 going that way. That so far makes 3, but then I can also go right down the middle here, 4, 5, and 6. How many sides did it have? It had 6. It had 6 lines of symmetry. This one has 6 sides, but only 2 lines of symmetry. Do you notice the difference between A and B? B is a regular hexagon. My regular polygons are going to have the same lines of symmetry as the number of sides. C is not a regular polygon, and the only way I could divide this one up would be 1 right here. Sometimes there are no lines of symmetry. I just wanted to show you how that does apply to even the real world. How many lines of symmetry does there appear to be in these? Well, this sheep right here, 1. Most of us are reflections of ourselves when we go across. And then we have this pentagon right here, which is 5. And then we have this little flower petal, which has basically 1, 2, 3, 4, 5, 6, 7, 8, and they're all about the same, which makes it regular, which means I would have 8 sides. I could go through and I could draw them all in. So I've got 1, 2, 3, 4 lines so far, and then again I can go in between each in between each set to get my 8, and then my 5 I could do the same. On lines of symmetry, we also, not only do we have lines of symmetry, which are lines of reflections, we also have rotational symmetry. That means, can I turn a figure so that it ends up back on itself? So if the figure can be mapped onto itself by a rotation of 180 or less, about the center of a figure. So when we talk about it rotational, we're going to talk about it being right in the center, and that's going to be my center point. So when it says center of symmetry right here, it's the point the figure is rotated about. It does not have to be the center point, but that's what we're going to look at. We're going to look at it being rotated about the center. Now in class, we're going to give you some stuff called patty paper. So if you want to use your patty paper, it might help you. I'm going to pause real quick and get set up to show you the next part that I wanted to show you. Okay, I'm going to show you rotational symmetry. I'm going to take this figure right here and I'm going to slide it. It's the same size parallelogram, or at least pretty close to. I'm going to slide it right on top. Now I can only do 90, 180, and 270 on this iPad, so there can be more, and that's where the patty paper helps you to see when there's more. So on this particular one, I'm going to take and I'm going to select that figure and I'm going to rotate it 90 degrees. Did my black parallelogram line up with my other black parallelogram? Nope. And unfortunately, I moved it just slightly. Okay, I'm going to take and I'm going to rotate it again, another 90. Now, remember, I accidentally got off a little bit, so I'm going to slide it down. So did that one line up? Yes. So far I've done 90, I've done 180, and I'm going to do it one more time. At 270, it did not work, and if I go one more time, it worked at 360. So does this one have a line of symmetry? Yes, the parallelogram has a line of symmetry, rotationally, not a line, at 180 degrees, because I turned it 180 degrees and it went back on self. I can't really show you the same thing on the octagon, but basically what you do is you take your 360, because that's what they'd all add up, and this has 8 sides, so when it's regular, you divide by 8, and when you do that, you get 45. 45 and 45 makes 90. 90 plus 45 makes 135 degrees. And finally, 180 degrees. I left out a little bit in my directions up here. A figure is mapped onto itself by, oh, I didn't leave it out right here. Rotation of 180 or less. So there can be more than one, like on B, 45, 90, 135, and 180 degrees is what it mapped on. Now I am going to pause for a second and get set up for the trapezoid to show you. Okay, I've now put a trapezoid on top of this trapezoid. I'm going to go and I'm going to select the trapezoid. I'm going to rotate it 3 times, 90, 180, 270, and you see if it ever went back to the same trapezoid. Nope, 90, 180, nope, 270, nope, 360, there it is. But remember, we're only interested in ones less than. So on this particular case, this one has no rotational symmetry. It would never, when I rotate it around, it's never going to be on top of itself. Okay, that is rotational symmetry. Okay, left the definition up here for rotational symmetry. I have this problem right here. It wants me to identify all the lines of symmetry and rotational symmetry of an equilateral triangle at the right. How many lines of symmetry are there? Well, remember I said if it was regular, which an equilateral triangle is, then it's going to have the same number of lines of symmetry. So there is 1, 2, and 3. So I know my answer is not A or B. I know it has to be C or D. At least get a 50-50 chance of getting something right when you take that into course test. Now rotational symmetry, remember if it's equilateral, we take 360 divided by the number of sides, which is 3, which is 120 degrees. If I had 120 and 120, I get 240. Remember, we want to stop at 180 degrees, so my correct answer would be D. When I take this and I rotate it 120 degrees, it will turn up to be right on top of the triangle, so it doesn't even look like it moved. Okay, now we're going to move on to translations. A translation is a transformation that moves every point of the figure the same distance in the same direction. Well, we're used to thinking of it as a slide. I'm always going to show you the coordinate notation in case the worksheets or the quizzes or the tests talk about translation. So a translation is taking a point, sliding it. If I'm going to slide it, I'm going to add A to X, and I'm going to add something to my Y. I called it B. So my coordinate notation is what I get when I add x plus how far to the right or left I moved it, and y plus or minus. So I'm going to pause, and I'm going to plot this particular quadrilateral. While I do that, you go ahead and do the same thing. Okay, now when I go to slide this, what my trans-coordinate thing is, it says 3 and a -1. So that 3 says move it to the right 3. The y value of 1 is a -1, so it says move it down 1. Okay, so right 3 and down run, so that means I'm going to take every single point and I'm going to do the same thing. I'm going to take point A, I'm going to move it 1, 2, 3 to the right, down 1. Remember, I call it A prime. B, 1, 2, 3 to the right 1. B prime. C, 1, 2, 3 down 1. And on D, 1, 2, 3 and down 1. So D prime. That does not look very much like a C. So then when I connect the dots, I get the same shape, just slid over to a different location. If my shape looks bigger or smaller, then I didn't plot a point right. Now I can also do this without plotting points by realizing to all my x values, I add 3. So if I look at point A, it says add 3 to 1, -1 plus 3 is 2, and then subtract 1 from y, 2 minus 1 is 1. So if you look at my new A coordinates, it's right there at 2, 1. So I could do that with every single point. So I can either list my points and then plot them. -1 plus 3 is 2. 5 take away 1 is 4. C, 4 take away 4 plus 3 is 7. 6 take away 1 is 5. D prime, 4 plus 3 is 7, and 2 minus 1 is 1. And if I counted each of my points, you'd see that's where they landed. So if you're a visual person, you can plot it visually. If you're one that likes to work with numbers more and then plot, you could do that as well. Okay, now sometimes they actually ask me to work backwards. So they told me that they gave me the image and x plus 4, y minus 7 is my translation. And they tell me the endpoints of P prime, Q prime. P prime is at -3, 4, and Q prime is at 2, 1. They want to know where the pre-image is. Where did I actually start at? So the way that I work this one is I have P prime at -3, 4. And what I really do is I want to work backwards, and I want to find out where P is. So originally, starting here, I added 4 to get here. So if I added 4 to get there, what do I want to do to get back? I want to subtract 4. So -3 and a -4 means I was originally at a -7. Right here at my 4, it said originally when I went this way, they wanted me to subtract 7. So when I go back the other way, I'm going to have to add 7. 4 plus 7 is 11. Therefore, my new P value is at -7, 11. Now we'll do the same thing with Q, only without the arrows. At Q prime, I was at 2, 1. So when I was at the original Q, I went 2, and I have to go backwards, so I subtract 4 and get -2. And Y, I originally subtracted 7, so to get back, I have to add 7. 1 and 7 is 8. So my new P, my original P was at -7, 11. My original Q was at 2, 8. Okay, now we have a theorem. You're going to be surprised. A translation theorem. It says a translation is an isometry. Remember what that means? It means that my figures hold their congruency. So on this one, what they did is they gave me a triangle and slid it to a different location, and they want me to write the translation rule. So that means my rule is going to be XY goes to. Now, what did I do to get back to the points? I have to compare like points. Notice my primes are the red one. My original one is the B one. So what did I have to do to get from this B right here to that B right there? I had to go left. So I have X. And since I'm going left, I have to subtract. So 1, 2, 3, 4. I went backwards 4. And then on my y values, I went from b to b prime. I went up 1, so y plus 1. So that right there is my coordinate form notation. Be very careful to pay attention that you're going from a prime to b prime. Okay, since translations have always came pretty easy to you, in geometry we extend them to vectors. A vector is a quantity that has both directions and magnitude and is represented in the coordinate plane by an arrow drawn from one point to the other. We're going to cover very quick basic stuff about vectors, and basically when you see vectors, it's basically a translation. It's just a simpler way of writing it. So first of all, our initial point is where we start at. Our terminal point is where we end at. So if we notice right here, F does not have an arrow, but G does have an arrow, so F is my starting point and G is my ending point. When I go to name a vector, I use the initial and the terminating point over it, and I use that FG with a kind of like a ray symbol, but only half of it. So just a quick refresher and remembering thing. Remember that if I have AB and I put a line over it, then it's line AB. If I just have a segment, then it's segment AB. If I have a ray, then it's ray AB. And finally, I just wrote another line. Segment AB would just be just like that. And now we have a new one. We now have our vector, whoops, which is just one arrow going up, vector AB. So we kind of do need to remember our terminology. So we name a vector by ending point to starting point, starting point going in the direction of the ending point with the vector symbol over it. This is our vector symbol. Our horizontal component is how far to the right or left we move it. So in this case, our horizontal component is a 5. Our vertical component is how far up or down we go. So in this case, we went up 3, so our vertical component is 3. Our component form is we take that horizontal of 5 and that vertical 3, and we write it like that. That is component form. So you have to know how to name a vector. You have to understand component form as well. So one thing to point out, I gave you this little thing in your notes right here. If you're talking about a vector, you better use these brackets that it goes in between, because if you use parentheses, you're talking about a point instead of a vector. So symbols are extremely important in geometry if you haven't caught on. Vectors use the brackets, points use the parentheses. Okay, and a point is a location of one specific spot, where a vector is just kind of a direction we're going to go in and how far we want to go. So even though it has an arrow on the end, it does not mean we continue going beyond that. That's where we're going to. That just tells me the direction. So component form is A comma B. Coordinate notation is when I write this whole piece right here. XY goes to X plus A, Y plus B. Component form, I just simply write A over B. I'm going to slide this up to give myself a little bit more room to write on and clear everything else off real quick. So down here, I want to move this up. Name the vector and write its component form. So I start with B, and I end at C, and I put the vector symbol above it. So there's my name. My component form, using these brackets right here, I went 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right, and then I went down 2, so that would make it a -2. There's my component form. On this one right here, notice my arrows at T, so that's my ending point. So when I name it, it's S going to T, using my vector symbol over it. My component form on this one is 1, 2, 3, 4, 5, 6, 7, 8, and I went to the left, so that makes it a -8. I didn't go up at all, which makes it a 0. Just so you kind of get the thing about component form and notation, if I wanted to do part B As coordinate notation, I would write xy goes to x minus 8, y. And y would not change. And again, those are points, so they stay with the parentheses on them. Okay, on this next part right here, I am not going to draw it or anything. I'm going to show you that we don't have to draw it. So I've now went through and listed all my points. I'm going to move it by my vector. So what my vector does is it says take 2 away from my x value. So I have 2 minus 2 is 0. And then I have 2 plus 6 is 8. Doing the same thing with my m coordinates. 5 minus 2 is 3. 3 plus 6 is 9. And finally, my last one, 3 minus 2 is 1, and 2 plus 6 is 8. That's using vector notation. It's just, again, a lot easier way to write it than coordinate notation. Okay, moving right along on to dilations. A dilation is a transformation that stretches or shrinks a figure to create a similar figure. The center of dilation is the point in which a figure is enlarged or reduced. We're going to look at them about the origin. Scale factor. We've had a little bit of issues with this in the last section we did on similarity. This is where the book truly defines scale factor, the way your end of course will look at it. It is the ratio of the side length of the image to the corresponding side length of the original figure. My coordinate notation for a dilation is my point goes to kx, ky. K is what we use for scale factor, so it just says I multiply my x value by whatever the scale factor is, and my y value, whatever the scale factor is. Now, do I get a reduction or an enlargement? If my k is between 0 and 1, in other words, meaning a proper fraction, then it is a reduction. If my k is greater than 1, then it is an enlargement. So again, that's where we got to pay attention. Am I getting bigger or am I getting smaller? Which way do they want me to do? So on my dilation, I'm going to pause right here and I'm going to plot my 4 coordinates A, B, C, and D. You do the same. So I just plotted my A, B, my C, and my D. I'm going to change colors to do the dilation of this particular one. For some people, the dilations are easier if they will write out their problems first. So I need to find A prime. They want me to use the scale factor of 2. That just says I take all of my points. 2 times 2 is 4. 2 times 1 is 2. My B value, B prime, goes to 4 times 2 is 8, and 2 times 1 is 2. My C value is 4 times 2 is 8, and negative 1 times 2 is negative 2. My D prime value is 2 times 1 is 2, and negative 1 times 2 is negative 2. Now I plot those points. So A moved to 0.42. So there's my new A value. B moved to 8, 2. So there's my new B value. C went to 8, negative 2. There's my new C value. And D went to 2, negative 2. There's my new D value. So my new figure is right here. Oops, I couldn't count my D. There's my 2. So there's my new D, going up to B, going across to B, going down to B. Did my figure get larger? Yes, I did. What shape is that figure? Everybody better be saying trapezoid. We have one pair of parallel sides, which makes it a trapezoid. Okay, my next one is a dilation, only this time my scale factor is going to be 1/2. So I'm going to pause and I'm going to plot the new one, and I'm going to figure out my A prime coordinates first and see if you match mine by you doing yours also. Okay, I've plotted my triangle A, B, and C. Now I want to get my coordinates for A prime, B prime, boy am I having trouble writing B's, and C prime. So A says I want a scale factor of 1/2. So is my figure, should it get bigger or smaller? That half, that's between 0 and 1, which should be getting a reduction. So half of 4 is 2, half of a negative 4 is negative 2. Half of 8 is 4, and half of 2 is 1. On C, half of 8 is 4, and half of 4 is a negative 2. So now I'm going to plot my points, 2, negative 2. There's my new A value. 4, 1. There's my new B value. And finally, C for -2. There's my new C. Did I end up with another right triangle? And I know it's a right triangle because my perpendicular lines, horizontal and vertical, always form right angles. So did it get smaller? Yes. So when I did my dilation, it did get smaller. Okay, I have a photo stickers right here. I want to find the scale factor. My photo is 4 inches by 4 inches. The image on the stickers are 1 by 1. What is the scale factor of the reduction? So since I reduced it, I know that my smaller number needs to go on top. So it would be a 1.1 over a 4. We never leave our fractions with decimals in them, so I need to make sure I reduce this. Easiest way to reduce it is math enter on your fraction, 1.1 divided by 4. The other way, if you don't have the calculator, you move your decimal once on the top, which gives you 11. If you move it once on the top, you have to move it once on the bottom. To do that, you have to add it in a 0, so 11 over 40 would be my answer. I want to talk about the 2 back here. What if the reduction, if your photo is 5 by 5, it's going to be basically exactly the same thing, only it would be 1.1 over 5.5, which becomes 11 over 55, which becomes 1 over 5. What I really wanted to talk about was question 4. Suppose a figure contains about the origin is dilated. Explain why that corresponding part on the figure is also at the origin. So if I were to take you back to the other dilations and you looked at the other problems we did, you'd notice that they got smaller, but they didn't really stay right on top of the other one. They kind of moved a little bit. So if I have a point that's at the origin, which remember is 0, 0, why would it stay at the origin? Right, because when you multiply anything by 0, it stays 0. So that would be why it would stay at the origin. Because my K0 and my OK is 0. My 0 times whatever my X value is and my 0 times my Y value would stay at the origin 0, 0. Okay, looking at the last problem, and I forgot to tell you, I think I flipped these 2 around on your paper that you had. Suppose quadrilateral PQRS is dilated to create the quadrilateral TUVW that is similar to PQRS. What are the coordinates of W? Well, first of all, notice that W is the last letter. That means it corresponds to S. So what I really want to get is the coordinates of S. So what are my coordinates of S? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay. Now, did they tell me the scale factor? No, they didn't. So I'm going to look at another set of points. I'm going to look at point Q, which was at 1, 1, and point Q moved over here to point U, which is at 2, 2. What did they have to multiply by to get the new value? They had to multiply by 2, so my scale factor is 2. So to get my new coordinates for W, I need to take my S coordinates and multiply by 2, in which case I get 10, 12. So C is my correct answer. If I were to try to plot this point, you'll see my graph isn't big enough to just be able to plot it. So what they were doing was checking if you could find the scale factor and then take a new coordinate set and multiply it by it to get the old one. This now concludes our lessons on transformations. I know we went through them real quick, but you should understand what a reflection is, flipping across the line, a rotation, turning about a point, a dilation, making it bigger or smaller, and also a, what's the one I left off? Rotation, translation, dilation, and reflections. So those are the 4 you should know about. Out of those 4, one of them does not have a theorem. Notice we did not have a dilation theorem. Dilations are not isometric. Dilations are similar. All the other ones are congruent. Reflections, rotations, and translations all hold congruency, but a dilation does not. It makes it bigger or smaller. Have a great evening.